Welcome back to the Deep Dive. We're here again, taking your notes, your research, all that curiosity, and turning into expertise fast. Today, we're digging into something fundamental, kind of the hidden engine room of software, algorithm performance. It's really core to any system that needs to work efficiently, especially at scale. We're not just shaving off milliseconds here. We're talking reliability, efficiency, how things scale up, performance, as all the material you send highlights. It means being fast, sure, but also using fewer resources and, crucially, handling growth without just falling over.
That's exactly it. That's the mission for today. We're looking through the technical stuff you shared, trying to understand how the best engineers actually measure the efficiency of these recipes, the algorithms that run basically everything digital.
Right.
So if you're building something new, or maybe you're just wondering why your favorite app sometimes, stalls, this is definitely for you.
Okay, let's start with a quick definition. An algorithm is just those step-by-step instructions the recipe a computer follows. Simple enough. But what makes a good recipe?
Well, like you said, it needs to be fast. It should use minimal resources, computer memory, that kind of thing. And really importantly, it has to be scalable.
Scalable. Okay. But the big question then is, how do you measure that? Objectively, I mean. How do you know if one recipe is better than another? Okay, let's unpack this a bit. When we first think about measuring speed, I think our first reaction, our gut feeling, is just use a stopwatch, right? Measure the execution time.
Yeah, that makes sense.
The actual time that passes from when you hit start to when it finishes.
Absolutely, and it's intuitive. We do it all the time in real life. Like, cooking analogies work well here. Pasta takes, say, 10 minutes. That's its execution time. Rice might take 20.
Or downloading files. A tiny file, maybe 5 seconds. A huge one, yeah, could be 8 minutes. Same idea, real-world time.
Exactly. That's execution time.
But, and here's where it gets really interesting, and why, computer scientists came up with something totally different. Why is using that stopwatch, that execution time, actually a pretty poor way to compare algorithms? Fundamentally unreliable.
Yeah. Because it's just full of variables. So many things affect that real-world time. If you run the exact same code on 2 different computers,
You get different time.
totally different times, or even run it twice on the same machine, maybe a few minutes apart, you could still get different results.
So comparing them scientifically is, well, it's basically impossible that way.
Right, and the material you pulled together, it really breaks down why. It lists these external factors, group them into 3 main buckets, I think.
Yeah, it did. Demonstrates why just trusting the clock doesn't work. Okay, first bucket, hardware. Obvious stuff, really.
Yeah.
How fast is the CPU? How much RAM does it have?
Yeah.
Is it writing to an old spinning hard drive or a fast SSD? All physical things that change the time, but they say nothing about how good the actual algorithm, the recipe itself, is.
Exactly. Then you've got the software factors. What language did you write it in? Python versus C++, say, for example, will give you massively different times for the same logic.
Okay.
And how good is the compiler? Like, how well did it translate your code? Even the operating system underneath it all makes a difference. Again, it skews the stopwatch.
So you could have literally the same perfect algorithm, mathematically identical, but one's running on, I don't know, a 10-year-old laptop, and the other's on a brand new server, freshly compiled code.
Why?
The times aren't comparable at all. You end up measuring the machine, not the method.
Precisely. And the last category is just environmental factors. The messy stuff. Like, is the computer busy doing other things?
Other programs running.
Yeah, or is there heavy network traffic, maybe slowing things down? What's the overall system load? These things change moment to moment. They're unpredictable.
So trying to use execution time to compare algorithm A and algorithm B is just futile.
Yeah, pretty much. It's too messy, too variable, just unreliable for comparison.
Okay, so if the stopwatch is out, we need something better, something more robust, universal, a metric that gives the same answer whether I've got tons of RAM or hardly any.
And that's where time complexity comes in.
Time complexity, okay.
And what's really neat here, I think, is that it shifts the whole discussion. We move away from the physical world, the specific machine, into the realm of mathematics.
Oh.
It's the ideal alternative because it's completely hardware independent. It abstracts away the CPU speed, the RAM, all that stuff. It lets you compare algorithms easily, objectively, and reliably.
So instead of measuring seconds on a clock, we're measuring
What?
the number of steps, the number of operations.
Essentially, yes.
Yeah.
The number of basic computational steps. And the standard way we talk about this, the notation we use, is called big O notation. You usually see it written as ON.
ON, right? The O stands for order of, I think, and the N What's the N?
N is key. It represents the size of your input data. So think of N as how many things you need to process, the number of users in your database, the number of files you're sorting, the number of pixels in an image. It's the scale of the problem.
Okay, so N is the size, and big O, the ON, tells us how the number of operations, those steps we talked about, how that number scales and it gets bigger.
Exactly. It gives you a formula, essentially. If N doubles, if your data doubles, does the work double? Does it quadruple? Does it barely change? That's what big O describes, the relationship between data size and effort.
Makes sense. But there's something specific about big O, a crucial assumption it makes. The material mentioned, it focuses on the worst-case scenario.
Yes, that's right.
The time the algorithm takes when it's running slowest, under the hardest conditions. Now, hang on. If we only focus on the absolute worst case, aren't we maybe, over-designing things, preparing for something that might hardly ever happen in reality? That's a really sharp question. And it gets to the heart of why this is, well, a computer science approach, not just casual coding. We focus on the worst case for a very important reason: guarantees, reliability, especially at scale. Okay, explain.
Well, imagine you're building, say, an online banking system, millions of customers. You absolutely cannot afford for it to suddenly grind to a halt just because some unusual situation, some edge case, makes the algorithm perform badly.
Right, that would be catastrophic.
Exactly. So by analyzing the worst case, Big O gives you a performance ceiling. It's a guarantee. It says no matter what happens, your algorithm will never take more steps than this predicts for a given N. That kind of insurance is incredibly valuable when you're designing systems that people depend on.
Okay, that shifts the perspective. It's not about the average speed so much as it is about guaranteed survival under maximum pressure. Makes sense. So now we get the N for data size, and we understand the worst case focus. Now we can actually look at the different big O types, the sort of hierarchy of speeds. This tells us if our code is lightning fast or painfully slow.
Yeah, this is where the rubber meets the road, really. We can finally compare algorithms based on their mathematical performance regardless of the machine. Let's walk through the most common ones, maybe 5 of them. From the best, fastest down to the slowest.
Sounds good. Lead the way.
Okay, at the very top, the absolute best you can get is O1. That's called constant time.
Constant time, O1.
It's the fastest because the number of steps it takes is always the same. It doesn't matter how big N gets. Whether you have 10 items or 10 billion items, the time is constant.
Wow, okay. So the workload doesn't increase at all with more data. How do you achieve that? What's an example?
The classic example is accessing an element in an array using its index. Imagine you have a huge list of things, maybe in computer memory, and each spot has a number, an index. If you know you need the item at index 500.
You just jump straight there.
Exactly, one step, O1. Doesn't matter if the array has 1,000 things or 1,000,000,000 things. If you know the address, you go right to it. Constant time.
Okay, that's incredibly fast. What's next down the list? Still very fast, I assume.
Next is O-log. This is logarithmic time. Still extremely fast, especially when it gets really, really big. The number of operations grows, but it grows very, very slowly as N increases.
Logarithmic, O log N. Why log? What does that mean in practice?
Think efficiency through division. The prime example is something called a binary search. Imagine you're looking for a specific name in a massive sorted phone book, like 1,000,000 pages thick. You wouldn't start at page 1 and read every name, right?
No, definitely not. I'd open it somewhere in the middle.
Exactly. You jump to the middle, see if the name you want comes before or after that page. Then you instantly discard half the book. And you repeat that. Jump to the middle of the remaining section, discard half again. Keep dividing the problem. For that 1,000,000-page book, you could find any name in about maybe 20 steps.
20 steps for 1,000,000 pages. That's amazing.
That's the power of O log N. The work increases very slowly, even when the data size explodes.
Got it. Okay, O1 is flat. O log N climbs very slowly. What's next?
Next up is ON. This is linear time. This is pretty common, and the performance is often quite reasonable for many tasks.
Linear. So if DON doubles, the time doubles.
Yeah.
A direct relationship.
Pretty much, yeah. It scales directly with the size of the data. You typically see this when you have to look at every single item in your data set at least once.
Like finding the largest number in an unsorted list.
Yeah.
You have to check them all.
Perfect example. Or calculating the average value in a list. You need to touch every element. If you have 100 items, it takes roughly 100 steps. If you have 1,000 items, it takes 1,000 steps. Predictable linear growth.
Okay, ON. Manageable for many things.
Yeah.
Now, things start getting a bit slower, I guess. What's after linear?
Well, there's a really important one that's slightly slower than ON, but still considered very good for complex tasks. It's ON log N, sometimes called quasi-linear time.
ON log n. So it's got the n part, the linear part, but also that efficient log n part mixed in.
Exactly. It's kind of the sweet spot for solving more complex problems efficiently, especially sorting large amounts of data. Algorithms like merge sort or quick sort, which are industrial standards for sorting, run in ON log N time.
So if you need to sort millions of items, this is generally the target speed.
That's the gold standard, yeah. It's more work than just looking at each item once, the ON part, because you have to compare items and move them around. But it uses clever divide-and-conquer strategies, the OMAN part, to do it much, much faster than the naive approaches.
Okay, ON log n, the sorting champion. Now we get to the slow ones, the ones to watch out for.
Now we hit the danger zone. The next common one is ONN, that's quadratic time, and this is where performance really starts to degrade quickly as n grows.
N squared. So if n doubles, the time quadruples. If n grows by 10 times, the time grows by 100 times.
Precisely. It gets out of hand very fast. And the scary thing is, it's often caused by relatively simple coding patterns. The most common culprit is nested loops.
Nested loops, like a loop inside another loop.
Yeah. Imagine you have a list of n items, and for each item in that list, you need to compare it against every other item in the same list.
Okay, so the outer loop runs in times, and
Yeah.
for each of those, the inner loop also runs in times, n times n squared.
That's it. If n is small, like 10, n is 100, no big deal.
Yeah.
But if n is 1,000, n is already a million operations. If n is a million. Well, you see the problem. This is how tasks go from taking seconds to taking hours or even days.
Okay, that distinction is stark.
Yeah.
O1, O long n, ON, ON log n. Generally good to great. ON, potential disaster at scale.
That's a good summary.
And this isn't just, theoretical math. Let's bring it back to the real world.
Oh, yeah.
The material had a fantastic example showing the actual difference this makes, the impact when log gets large.
Oh, yeah. The sorting example with a million elements, it really drives the point home. The difference between choosing a good algorithm and a bad one is just massive. Okay, lay it out for us. Scenario A, the bad choice. Okay, scenario A, we try to sort that array of 1 million items using an ON algorithm. The quadratic one, the slow one.
So n1 million, what's n squared?
1 million times 1 million is 1 trillion, 1 T operation.
1 trillion steps. What does that mean in terms of actual time?
Even on a pretty fast modern computer, we're talking hours, maybe many hours, possibly even longer, depending on the specifics.
Yeah.
Just not practical for most applications. Hours. Just to sort a list. Okay, that's clearly bad. Now, contrast that. Scenario B, the good choice, right? Scenario B, we use a much better algorithm, an ON log n, one like merge sort or quick sort, the industry standard.
Same n, 1 million items. What's the calculation now? N log n.
Well, log base 2 of a million is roughly 20. So n log n is about 1 million times 20. It's around 20 million operations.
Okay, wait. From 1 trillion operations down to just 20 million?
Exactly. A massive, massive difference.
And what does 20 million operations mean in terms of time?
Instead of hours, you're looking at seconds, maybe a few seconds at most on a typical machine.
Wow.
Thank you.
That's incredible. Hours versus seconds just by choosing a different mathematical recipe.
He really highlights why understanding Big O is so critical.
I actually remember hitting this exact problem early in my career. We built this report generation tool. Worked fine in testing, the few hundred fake records.
Mm-hmm. The classic trap.
Yeah. Then we pushed it to production. First real run with maybe 50,000 customer records. It just died. Locked up the entire server for almost 2 hours.
Ouch. Nested loops.
Textbook ON nested loop.
Mm-hmm.
Totally fine when ON was small. Completely explosive when the real data hit it. Cleaning that up was not fun, but a very valuable lesson.
That's a perfect illustration. Algorithm choice is absolutely paramount. It's the difference between software that scales gracefully and software that just hits a wall. It can turn that multi-hour nightmare into something that finishes before you even blink.
You might get away with, say, an ON linear scan for checking a small config file, maybe.
Sure, for small n, the difference might be negligible.
But the instant you're dealing with user data, transaction histories, anything that could grow, you absolutely have to be thinking in terms of ON log n or O log n, or even O1 if possible.
You really do. Otherwise, you're building on shaky foundations. Okay, so let's quickly recap the core difference then. Execution time. That's the stopwatch time, actual seconds passed. But it's unreliable for comparison because it depends on the hardware, the software environment, all that stuff.
Right.
Too many variables.
Whereas time complexity, which we measure using big O notation like ON or ON, That's the mathematical measure. It counts operations relative to the data size adjoints. It's hardware independent, objective, and lets us reliably predict how an algorithm will perform as the data grows.
Couldn't have said it better myself. It's about understanding the inherent efficiency of the recipe itself. And connecting this back to the bigger picture, I think the source material put it quite powerfully. The algorithms you use determine the future of your software. That's a strong statement, but based on that ON versus ON log n example, it feels accurate. Choosing the wrong algorithm can literally break your application when it needs to scale. You often can't just fix it by throwing faster hardware at the problem indefinitely.
It really does make you think differently about the software we use every day, all the hidden calculations happening underneath. Which brings me to a final thought for you, our listener, to maybe ponder. Given that truly enormous difference we saw between ON log n seconds and ON hours, how often do you think in our everyday tools or systems we might be running inefficient, maybe ON algorithms, simply because the amount of data, the N, hasn't gotten big enough yet to make the slowness unbearable?
That's interesting, like lurking inefficiencies.
Exactly. Slow recipes hiding in plain sight because N is still small. And what happens when that data inevitably grows? When does the ticking time bomb of ON finally go off?
Yeah.
Something to mull over until our